Welcome to our chapter. This is chapter F5.2 on zonal statistics. I'm Sarah Winsemius. I'm a PhD candidate in ecology at UC Davis, and I study forest and fire ecology. And Justin, you want to introduce yourself?
Yeah, sure. I'm Justin Broughton. I'm with Earth Engine Developer Relations team. It's nice to be here with you, Sarah. Sarah and I met back in 2019 at AGU, and we talked about zonal statistics at that point, and then made a community tutorial about it, and it eventually turned into this book chapter. And a lot of the material that we just heard from Keiko and Samuel are relevant here. They had a lot of great graphics. Sarah and I have less graphics. It's more about tabular data. So it was nice to get sort of a warm up from Keiko and Samuel. Thank you.
Yeah, absolutely. All right, so the outline is the same as usual, chapter overview, and then we'll go into the theory and the practicum. We have a few examples. So basically, this chapter is about extracting values from rasters for intersecting polygons to calculate zonal statistics in those polygons. So our learning outcomes are to learn what zonal statistics are and how to use reducers, buffering points as square or circular regions, which we did a little bit in the last chapter, writing and applying functions with optional parameters, exporting those computation results to a table, and copying properties from one image to another. And the references to previous topics are understanding the distinctions among raster and vector data, which is in that last chapter. In Earth Engine, these are images, image collections, features, and feature collections. We'll use drawing tools to create points, lines, and polygons, or you can upload your own. And we'll write a function and map it over a collection, and then we'll export these calculated data to tables in the tasks tab. So the theory, so what are zonal stats? I'll use the example of a field plot here, although there are many applications. This is a photo here that I took of my lab mate and her field assistant collecting plot data in a beautiful subalpine forest in the Southern Sierra. Very fortunate to work there. You can kind of see a transect tape on the ground. So if you think about a plot, in this case, it has a center and a radius, and that center may also have some positioning error from the GPS in the field. So you go and you take data in the field, and then afterwards, maybe you want to extract some other kinds of data for that plot, maybe topography, reflectance spans, or vegetation index like NDVI or normalized burn ratio, or maybe climate data. And then you want maybe these also in a time series as well. So you could take the center point value for that plot and extract that, but depending on the spatial resolution of your imagery, the size of your plot, the positioning accuracy of your GPS, that single pixel value may not actually be representative of the conditions within your polygon. And it might make more sense to take a statistic of a group of pixels, and that's what these zonal statistics are. So the output that we're doing here is a table with rows for each image and plot combination. This allows you to do time series. And then you can export this to do analyses or graphing in R or Python or something. And as we know, the way to do zonal statistics in Earth Engine is with reducers. So there are weighted and unweighted region reductions. And this slide, the info in this slide is actually covered at the end of the chapter, but we're bringing it up here because it's actually pretty important and relevant to the theory. So a question that came up for us when digging into this topic was how partial pixels are treated. And that depends on whether you're using a weighted reducer or an unweighted reducer. So a weighted reducer includes every pixel that's covered by the polygon, and each pixel's value is weighted by the relative fraction that intersects that polygon. So here in this image, any pixel that overlaps, even these little corners here, would be included in the overall value that you're calculating, but just a very small amount would be weighted for that little piece, and a lot more would be weighted towards this one and this one. Weighted reduction is the default for mean and median in Earth Engine, among others. And also you can make what's normally a weighted reducer into an unweighted reducer with a separate call. An unweighted reducer then assigns equal weight to all pixels whose cell center intersects the polygon. So in this case, it would be these 3 pixels where the pixel center is marked. So you would have these 3 pixels considered. An unweighted reducer is the default for min and max. So in this case, if you were taking the maximum for this polygon, you would get whatever value the maximum pixel is, probably this one here, looks the darkest. Or maybe it would be this one, I don't know. I don't remember the scale, the colors. So you would get that value, whatever is the minimum or the maximum for that. Or if you were to make an unweighted mean or median, it would be the mean or median of those 3 pixels only, and they would be weighted the same. So for unweighted reducers, it's especially important that the polygon size be appropriate to your resolution, because too small a polygon relative to your pixel size may return no data for some of those plots if the polygon doesn't cover a plot center. And there's code at the end of this chapter where you can count the number of pixel centers per plot and also plot them as you see in the screenshot. So now we'll move on to the practicum with Justin.
Thanks. Share my screen. All right, so we're talking about zonal statistics, and Earth Engine has a couple of built-in functions to do zonal statistics. We have reduce region and reduce regions, and they both operate on a single image object. The difference here is that reduce region is working on a single geometry, and reduce regions will work on a feature collection. So you get statistics for all of the features in a feature collection. And so what you get back from the most simple version here, you've got a single image, let's say a DEM, and you have a single polygon that would be appropriate for reduced region. You'd get back a dictionary that would contain whatever statistic you wanted for however many bands there are in this image. With reduced regions, we give it the feature collection, which is maybe our plot centers, or if we have protected areas, like in the last presentation, we wanted to know something about the image pixel values in each of these particular regions. We would use reduce regions, and we'd get back the same feature collection, except now each of those features in the collection has a set of properties that are the statistic for each band in this image. And so these work great sort of out of the box for an image object. But if you want to do a time series, if you want statistics over a time series, it requires some more work. You have to map a function over an image collection. So you have a series of images, and you basically do a for loop. For each image in your collection, you would run one of these functions, and then you have to kind of reassemble the results into, or sort of collapse the results into a single feature collection. And so a big part of our tutorial is on how you can take those two functions and make them into a more usable, sort of reusable function for doing time series work as well. So right, this is an example of just a single image, and we can run Earth Engine's functions right out of the box to get statistics about something in that image. But if we have the time series, it becomes more complicated. We have to map those functions over the image collection. And so this is an example just pared down of what that might look like if you had this long time series of, for instance, Landsat imagery, a composite per year. How would you get a table of statistics for plot centers so you could understand how your field study sites were changing over time according to the Landsat time series? So let's just break this down a little bit. We have an image collection. We could imagine that this is a Landsat collection, maybe one image per year. And then we're going to map a function over it. We're basically going to do a for loop on this image collection. So for each image, we want to do something to it. So we write a little function that we want to run on each image. And at each image in the collection, we're going to run reduce regions. So reduce regions assumes that we have a feature collection. We have a series of plots or features or polygons that we want statistics for. And there's a set of parameters, where we could define the scale, the projection, some other optional parameters. And at each step, at each image, we're getting back a feature collection. So we're returning a feature collection at each step. And so what we get at the end is a feature collection of feature collections, which is a strange thing to work with. And so what we do at the very end is we flatten it into a single feature collection. And so you could do that on your own. What we wanted to do in this tutorial was make a function that could be really reusable. You could just copy and paste this function into any script that you were doing zonal statistics on, and you'd be able to produce results without having to write your own code to do it. This could also be something that you would put into a module. If you're familiar with Earth Engine's require function, it allows you to, for instance, save a script that would have this function in it. And then when you call require, this function becomes available in whatever script you've called it into. It's a way to not have to copy and paste code around, similar to libraries that you would load in Python or R. You would just call whatever function happens to be in those libraries. So you might want to do that with this function. So let me just walk through what this reduce regions or this zonal stats functions does. So I'm in the code editor now. This code is available in the chapter. I'm on checkpoint 2B here. We forgot to mention, this will come into the next part, maybe for Sarah, but we have a buffer points function here that is just a helper function in our tutorial to expand the size of a point collection. But this is what I'd like to talk about, is this zonal stats function. So the parameters are an image collection, for instance, a Landsat time series. The feature collection, we could imagine it's a series of field plots that we've visited and we want to collect information from Landsat about those points. And then we have a set of optional parameters. So then if we dive in, we have all of the parameters here at the top that are available to this function. And so we set some as default. So the reducer for this default, the default reducer for this function is mean. We don't set scale, the CRS, the bands of the image. A bunch of these we just consider null when we're setting these default params. They get filled in later on. And I guess one thing that we wanted to do with this function is make the property names easily changeable, so that when you're working in R or Python, like once you have taken the results out of Earth Engine, you've made a CSV file. If you don't like the property names that you get out of Earth Engine, you can easily change it here to make it more intuitive as you work with it in some other platform. So there's these parameters for like taking image properties as they are in Earth Engine and renaming them. So you provide a list of property names that you want to be included in your table. So Sarah mentioned that when you do these statistics, you get a row for each combination of image and feature. And it might be helpful to have information about the images what was the date, what was the sensor, if it's Landsat, was it Landsat 5, was it Landsat 8, what was percent cloudy, what was the quality. So we can include all of those image properties in the table that we export in, besides the statistics that we get out of it. And so we can name all of those additional image properties as we like. We also have properties for the date time. This is helpful if you're plotting and charting in R and Python to have some timestamp associated with it. So we include the date time, which is milliseconds since unique epoch. And then also you can provide a human readable timestamp. So that was a lot about default parameters. Sorry about that. So you can accept them as they are, or you can specify what they are. If you don't specify what these kinds of properties that you want from the image are, it'll just take them all from the image that it's working with. That's what this section is doing. It's filling in all of these nulls with actual image properties. If you haven't specified which ones you want, it'll just take them all. And then we get to the heart of this, which is the region reduction. So we have our image collection, we map a function over it. And so this is the for loop. We're now working with a single image at a time, and we're going to select bands that you want information for. You don't have to take whatever's in there. You can select out whatever you like. And then we're going to set some image properties for that image. This section here is defining the final image properties so that when we get our table at the end, we'll know all the information about what statistics came from what image. And then we subset the features. So if you have, point collections, you have field sites that span like multiple states, a single Landsat image will not contain them all. So what we do in this step here is we only work with the features that intersect the image, the image currently being worked on. And then we run reduce regions with the parameters for scale and CRS that come from the image that it's working on currently. And it uses the reducer that you've specified, or else the default mean reducer. And then we add, so what we get from this is a feature collection. And then we add to that feature collection, all of the features get the image properties tied to it. And then at the very end, we flatten the feature collection of feature collections and return the giant table, or possibly giant table. Yeah, so we'll be using this function throughout now. It's more complicated than it needs to be to get zonal statistics, but we thought that this would be a helpful, reusable piece of code. And if you're interested in building your own types of reusable sort of generic functions, this might be a good template for you to go off of. Yeah, so thank you. And I'll pass it back over to Sarah, who will talk about using this in an application.
Yeah, thanks. So let's see, should be sharing now. So our first example now is on topographic variables. This is the simplest application in R3, and it's for a single multi-band image. So if you see my code editor now, I'm still in that 5.2b checkpoint. So as Justin mentioned, we have this buffer points that takes a radius and bounds. And then we also in here add points as a feature collection manually, but you could also add them as assets and load your points that way. You could also load a polygon file. You don't have to use the buffer, and you don't have to load points manually if you don't want to. But for the point of our tutorial, this was the easiest way to do it. And we gave them plot IDs so that we could keep track of the identity of each plot. So in our first example, the topographic variables, we buffer our points. You could also, at this point, just load your polygons. We import an elevation data set that's a DEM, and then we calculate slope. So you could do this just as a single band, or you could add multiple bands. You can process your images, and all of that is fine for pre-processing. So just a single pre-processing step on this one, and then we concatenate those two bands together into still an image, a single image that has two bands. And then we wrap that into an image collection so that we can apply it to the zonal stats function. This is important for being able to map the zonal stats function over multiple images, but you can also map over a single image. And then we define the parameters. Here we take the bands, which were 0 and 1. That wouldn't be very helpful when you export it. And so we rename them using this bands rename. So like Justin said, there's a lot of different things you can modify about this function, and that's just to make it as flexible as possible so that it's really easy to reuse. And then you just run the zonal stats function on it. So you call the topography image collection, your points topo, which is our buffered points feature collection, and then the parameters. And because parameters doesn't specify a different reducer to use, the mean is the default. So it'll just calculate a mean. And then we have it printed to the table. So this is just the feature collection before anything has been exported, or anything has been calculated for it. The topo zonal stats table, if you go in here to properties, you can see that it has that plot ID. That's so you can keep track of what your plot is or what your polygon's identity is. And it has a slope that would be mean and a timestamp. Oh, an elevation. And we also added it here to the map so we can see it. And if I zoom in, you can see that we've got the point in purple. It's not zooming more. There it goes. We have the point in purple, and then the buffer is shown in yellow. So you can see that that mean would be a combination of those 4 pixels that it covers. Yeah, also, let's see if I go back to our slides. So the output is a feature collection, which is basically a table. And we have the plot ID, the time, which is just the date of when the DEM was assigned, collected. Probably wasn't actually collected at midnight on January 1st, but that's the data. That's the date that's in the data set on Earth Engine. This will be more important for the imagery, which actually does have useful date time information. And it has our mean elevation and slope, which I just got rid of some of the significant figures because there were a lot. And so that's the output for a single image that's been made into an image collection. And then Justin will go over our 2 more complicated multi-band examples.
Yep, so now we're on to time series. So in Sarah's example, we had a single image, the DEM. And in this example, we're going to dive into sort of the most basic time series we could come up with. There could be
Justin?
others. Yep.
Sorry to interrupt. It says you've started screen sharing, but it's not working. Could you maybe, oh, now I can see it. Never mind.
Okay, thanks. Yeah, so to start out here, let's show an example of a modus time series, and this is sort of the most basic one that we can show, I think. So this modus data, I forget exactly, but it looks to me like it is surface reflectance over a period of time, maybe 16 days, maybe a 16-day composite. In any case, the MODIS team have this data product where they have removed clouds, done some quality assessment, and then made kind of a best pixel composite for these time windows, maybe 16 days. And so that's what we've got here. We've loaded up this image collection of MODIS data. We're going to take, we're going to filter it to 2015 to the end of 2019. And we're only interested in summer dates in this case. And so what we want is a time series for these points that Sarah showed in the previous example. We want to get some information about the reflectance, the summer reflectance over 5 years, maybe how that changes over time in these 5 plots. And then we set parameters for this function I talked about earlier. In Sarah's example, we didn't set the reducer, but we are now. We're going to use the median instead of the mean. We're setting the scale explicitly at 500 meters. We're also specifying the projection. And like in Sarah's example, we're going to rename the bands. So this is the list of bands that we want information for. We want the median over time for. And the band names don't mean that much to me. So if I saw these later in a table a month from now, I would have to look up what these mean. And so what I'm going to do is I'm going to rename these bands to be more self-evident. When I see the field name in the table, I'll know that, I'm working with red, near infrared, and shortwave infrared. I'm going to name the date column date, and this is the format that I want for the image dates, the time series. And then those parameters are fed to the zonal stats function we built earlier. I give it the MODIS collection that is filtered out to the things I like, and then I give it the points, which I think, in this case, we're buffered out 50 meters. So, they're smaller than a MODIS pixel, which we've set here at 500 meters. So when we run this, what we get is a feature collection, and I've limited it to 50 features here just to save us a bit of time in printing. And let's take a look at what we get back. So it's a feature collection, and we can see that as part of this name, this feature is associated with the MODIS image from 2015, July 4th, and then we have the plot ID. So this is giving us the median for plot 0 on July 4th, 2015. And we can see that there are 5 points here with this date. So all of our 5 points now have an observation or statistic for this July 7th MODIS image. We can see that there's also one for the 12th, 5 points with observations from the 12th, and so on. And if we look at the properties, we can see that we now have the median of this buffered point. We have the median for near infrared, red, and shortwave infrared. We know that this is for plot ID 1, and we have information about the timestamp, when this MODIS data, when this MODIS observation was taken. Or in this case, since it's a composite, they've maybe set the date at the middle, beginning, or end of the composite date range. Anyway, this is just the date that comes from the image that was being worked on the data catalog. So this is a real simple example of how you could get zonal statistics for a time series of data. But let's also talk about a more complicated example where you would do some image prep before getting your zonal statistics. And just sort of to be helpful and practical, we did a Landsat example here. You could just copy and paste this code out and probably use it in a lot of your own applications. Sentinel-2 is also popular, and it would be similar to this. You might mask clouds, you might do some band renaming. So hopefully this gives you a place to start if you're interested in time series tables for Sentinel-2, and in this particular case, Landsat. So Landsat imagery, what we'll be working with is just the raw imagery, no composites. So we're going to make our own, we have to do our own cloud masking. You wouldn't have to, but in our case, we didn't want cloudy observations to show up in our table. So we're going to mask out clouds. We have this mask function, which uses bands from the surface reflectance product to identify pixels that are either cloud, snow, or shadow, cloud shadow, and then also saturated pixels, which are typically cloud related as well. And then we also scale the Landsat bands so that they are in their proper unit. So when we look at our table at the end, our time series table of reflectance, it's in the expected units. And then at the end here, we apply the masks to the imagery. So we get back now an image that is properly scaled and has been masked. Clouds and cloud shadows have been masked out. And then we have two functions here to get the band names of Landsat to be consistent. So we're going to include in this time series Landsat imagery from I believe, Landsat 5, 7, Landsat 5, Landsat 7, Landsat 8. And so Landsat 5 and 7 have different band names than Landsat 8. We want consistent band names, so we have these functions to do renaming. And then we have two wrapper functions that will prepare the OLI data. So the first part here is to apply the mask and scaling function. Second, we rename the bands. And then we have a similar setup here for the ETM data. Here we load our points data set. Prepare our points data set with a 15-meter buffer. This would be a place where you might import your own polygons or points. Instead of having this variable, it would be whatever you selected or imported. And then we load up the OLI imagery, the ETM plus imagery, and the TM imagery. We filter them to the bounds of whatever feature collection we're working with, and then apply the prepare function. So we mask clouds and we rename bands to all three of these sensor products or sensor collections. And then we merge them into a single collection. And then we set our parameters. This is the same as above with Modus. We tell it what reducer we want. In this case, we're just going to set it to max. And then set the scale, projection, do some band renaming so that, I'm not sure why we did this one in this case. The original ones make sense too, but there it is. And then we're going to pull out, so there's a whole bunch of image properties that come with a Landsat image, and we don't need all of them to be in our result table. So the only information we want from the original images are the sensor ID and what satellite it was on. And we'll rename those pieces of information, those fields, to be what we would like here. We call the date field date, and that's the format that we would like the date in. And then we apply our zonal stats function using all the parameters and our image collection that has been processed now. And this is also a new addition here. So because we have now masked out clouds, there's potentially no data in these images where our points intersect. And so we get back, nothing for those zonal statistics where there's a masked, where it's all masked. And we're not interested in that. So what we can do is we can filter this result to include only not null. It has to be valid values is what we want here. So if we take a look, again, I'm just reducing or limiting this to 50 observations. And so what we can see here, this is similar to the MODIS one that we looked at earlier. We have the Landsat image, and then we have the plot ID. And we can see in this case that we only have one observation for this date, 2013. It's an OLI image from 2013, May 13th. But recall that we have 5 features. And what has happened here likely is that in this date, these other features that are not here, they were intersecting masked pixels. So we've gotten no result because we have filtered them out. I think if we comment that out, yeah, we can now see that for May 13th, there are now 5 observations. But if we look, we can see that there's no band information for this particular date and plot. So by calling filter null, we've gotten rid of those rows that have no data. And so what we've been doing right now is we've been using the interactive Earth Engine's computing stack. And so we get results right away. We can inspect them and view them. But if you want to work with these data outside of Earth Engine, you're going to want to export them to Drive or to cloud storage, and you can write out these results as a CSV file. So recall that the feature collection is essentially a table. Sarah showed you that graphic earlier. So what you get back is a CSV file. And it's also important to note that the interactive stack, what we're viewing now here sort of in real time, is limited. You can only print 5,000 features, and it's limited to 5 minutes of compute time. And if it goes over that, it times out. And so if that's the case, if you're getting a timeout or you have more than 5,000 features that you're trying to print, you're going to need to use the batch task. You're going to need to export either to an asset that you load back in later after the task is completed, export task is completed, or to Drive or cloud storage. Yeah, so Sarah, do you mind showing us what the result would look like if we wrote this to Drive?
Yeah, absolutely.
Thank you.
So once you open it in Drive, and this is just in the folder, you can see that there's date, image ID, this is that sensor ID, and we have each of these bands, our plot ID and the satellite and this timestamp. But if you open that as a sheet, then you can actually look at it a little bit more closely. You can sort this by, see, I did it earlier. There it is. You can sort this by date, and you can see that it actually does start in 1984 with the thermal mapper and Landsat 5. And so you can see also that these dates still were missing some because of that removing of null values. And timestamp, well, that's the Earth Engine timestamp thing. But then we have this this date that we formatted as we wanted it. And yeah, then you can take this and work with it in R or Python and make pretty ggplot graphics and analyze it. And yeah, this is what I was trying to get when I first approached Justin about trying to do zonal stats, is that I was trying to get a time series of Landsat. Yeah, we wanted to make this available to everyone with all of the Landsat processing steps, because there's quite a bit of stuff to do before you actually use it. And Justin, do you want to talk a little bit about copying properties also? Image properties?
Yes.
Or I can...
Yeah. In all of these examples that we have shown, we are not generating any new data. We're not deriving any data. We're just using existing Landsat bands or MODIS bands or DEM bands and calculating statistics for them. And so when we are building these tables and we're including, for instance, the date or the sensor ID or the spacecraft ID, as a field in our table, it works fine. But if you are, for instance, wanting to calculate NDVI or normalized burn ratio from a Landsat image, you would maybe have another function. Oh, I'm moving my screen around, but I'm not sharing it. 1 second.
Oh yeah, I pulled up the screen also, if you want to share.
Okay. Is it, you see it now?
Yeah.
Great. Yeah, so right, we're talking about image properties, wanting to include different image properties in our exported table. So in this last example, we wanted to include the sensor ID and the spacecraft ID. These are specific pieces of information from each individual image. We want to include them in our exported table. And this works fine if you don't alter the image. If you're working with a non-computed image, all these properties that you like would be there. But if you're deriving something like NDVI or let's go with NDVI. If you're calculating NDVI, you are computing a new band. And if that is what you return in any of your image processing steps, for instance, we have this mask and scale function. If also in here we calculated NDVI, we had NDVI, and then the expression for that. And what we did is only returned NDVI. All of the image properties would be lost. Any information about the date that it was taken, any information about the sensor ID, the cloudiness of it, would all be lost when you generate this computed image, because we can't assume that those properties are still valid. So we just don't assign properties. And so it's important that if you are deriving a new band and that's all that you're going to return, that you copy properties, and you can copy them from the input image, and you can tell it what properties you want to copy over. Another thing that you could do is you could take the input image. So you'd have your input image, that's the image that we get working on currently, and it includes all the original information. We could select no bands, and then we could add bands in NDVI. Oops. And that would also then retain all of the image properties. And this is actually faster than doing the copy properties method. Geometries, if they're large, can bog down the copying bit of it. But this, by selecting none and adding bands, we get around having to copy and move things around. Yeah, So if you're making derived images, be sure to keep track of your properties and make sure they're retained. That's that.